Okay, let me double check. Okay,
Okay, let me double check.
okay. So this is a podcast online course for the topics on advanced mathematics 这个数学物理专题but the name is actually not very appropriate. Okay, hi, hello, Janice. Okay, so I'm going to lecture for 1 hour today, just probably just 1 hour. This course is designed to prepare students, well, already with quantum field theory backgrounds, some of the topics they will need when they do research in particle physics. Okay, and I designed it so that it is not really it's not really could stand alone, I should say. I choose several standalone topics that will be useful. For example, today I'm going to talk about gauge theory, gauge field theory. And next week, probably I will talk about the bispinner Dirac Lagrangian, for example. And so you can see that they are not very systematic. However, that's exactly the point. So again, course is designed for those who already have a quantum field theory background. So quantum field theory is a very systematic exposition about how we can calculate in particle physics. So those of you who haven't took quantum field theory, you are you except for Janus, then you are encouraged to participate in Professor Chen Chuanren 老师. Professor Chen is going to offer quantum field theory this year. Okay, so and we really need you to know how to write Feynman rule and how to write down draw the Feynman diagram and write down Feynman rules. And I'm not going to go back to cover those topics. Okay, so that's why we will need you to at least have some knowledge about quantum field theory. Okay, otherwise, I don't think you are going to understand what I'm talking about. Yeah, because I'm going to jump directly into those topics after quantum field theory. And usually for a particle physicist, after quantum field theory, the research topic becomes diverse. Okay, that means you can go this way, you can go that way. And so that's why usually we don't have a unified course for those advanced students. Okay, that's why, and usually professor and faculty member will pick some of the topics that is useful to their institutes. For example, here probably I will talk about dark matter. I will talk about neutrino mass. Maybe next term. Okay, next semester I'll go into some of these topics. Okay, yeah. So so that's why I call them the standalone topics. 好的，独立的一些题目哈。Standalone topics. They are not really related, but as a whole, they constitute the knowledge you will need to do elementary particle physics. Okay. Okay. Now, so that's the idea. So I can briefly tell you what I want to cover in this course. Uh, Today, I'm going to start with gauge theory, because I think because for this semester, the topics on advanced mathematics, I really want to cover standard model, at least for the first half of the semester, because because quantum field theory course usually don't cover standard model. That's very strange because the standard model is one of the most beautiful quantum field theory, and that is useful in nature. However, nowadays quantum field theory has been taught also to students in condensed matter theory, and also maybe in cosmology. Therefore, the quantum field theory becomes very, very diverse, not just for particle physics. Unlike in the old days, it is designed for particle physicists. So that's why we I don't. So usually sometimes the standard model for particle physicists become a very, very small chapter in the course of quantum field theory. Okay, you can check most of the useful quantum field theory book, including the one Professor Chen will use this year, the Rider. It is a quantum field theory book. Now it has been talk about a lot of things like a path integral, etc. However, I don't think I checked yesterday. It does not cover standard model. Okay, so that's why and part of the reason is that these authors expect students to go on to took another advanced quantum field theory course. Okay, so just like I'm going to give today. Okay, some kind of advanced quantum field theory. Yeah, so that's why they did not cover it in the elementary quantum field theory courses. But that's fine. So that's why I think this course will offer some will be useful, especially for example for Janus and for David, 张大卫 especially two of you. I think I'm going to talk about some of the topics that is useful. Let me say it in Chinese for a little bit. 那对于其他的学生，我觉得这个课程可能对你们来讲并没有用处哈。原因就是因为这个虽然题目叫做数学哈，但是呢，事实上我们不是在系统性的谈数学啊，因为题目上面就是专题嘛 ，topics。OK， 好，所以呢 ，again 我刚刚已经讲过了，如果没有量子场论的基础的话，你就没有办法听懂我在讲什么哈，因为设计上就是希望能够让这个已经准备要做粒子物理研究的这个同学哈，再进一步的得到进一步的这个最后的一个知识。那你如果不是要做基本粒子的同学，即使你可能是要做高能啊，比如说弦论啊什么，可能不见得真的很有用哈，因为呢，现在这些各不同的科目呢都已经慢慢分开了。OK，so that's why 所以呢。所以呢，这就是为什么要跟大家抱歉哈。虽然这个题目听起来好像是跟大家说，可能大家有点误会，听起来好像是在讲这个数学哈，但是呢，我们的确是在讨论数学，只是说它可能是在这个对粒子物理呢比较有用的这个方面哈，所以这个要先跟大家说抱歉哈，先跟大家说抱歉。In the past few couple of seconds, I was telling the students that this course is only for particle physics. It's useful only for particle physicists in a certain sense. Okay, so probably so so when I teach, I probably is looking at Janus and David as my audience in a way. Okay. Now, gauge theory. Okay, standard model. So the standard model will be the topic for the first half of the semester. So to understand the standard model of particle physics, of course, you need a gauge theory. Okay, so that's why I choose the gauge theory or gauge field theory to start my lecture today. And in gauge theory, I'm going to so this is I try to choose some material from standard textbook because we cannot do it in class, so I don't have a blackboard to write formulas. Therefore, I need a textbook with more or less all the formulas in it, so that I can just point my pointer to show you all this and that. This term, add that term, give you this, blah blah blah, and that means you will probably have to do the exercise at home yourself. David probably have done it before already, because this is the part of the quantum field theory you took in Taida. But Janus, probably you need some time to do the derivation, because I don't have a blackboard here to show you the detailed calculation. However, I think you can do it anytime, and this textbook actually offer almost all the connection between calculations. So it's a very, very, very good pedagogical textbook. Amazingly, this is actually from very old days. Not that old. I mean, it is actually the one from which I learned gauge theory. It's written by Zheng Dapei and Li Lingfeng. Li Lingfeng is a physicist from Taiwan, and he is one of the first pioneers in this gauge theory thing. And he popularized how, so that almost all the particle physics, in the beginning, particle physicists or physicists don't understand what gauge theory is. Okay, so it takes some time. It takes probably 10 years for people to get familiar with the language of this, the mathematical language of this thing, so that they can describe elementary particle physics. Okay, yeah, and so Li Lingfeng, Professor Li, was one of the pioneers to popularize these topics. Okay, and this is the textbook he wrote with Professor Chen from Pittsburgh University. Professor Li is in Carnegie Mellon. Okay, so and I think it's very, very pedagogical. And after so many years, I try to find a textbook. I mean, people wrote a lot of other textbook, and they talk about gauge theory. But gauge theory is a very, very sophisticated thing, because it is mathematically very difficult. Part of the reason is that the gauge theory is not just the symmetry. We usually call it a gauge symmetry, or call it local symmetry, as I will demonstrate to you later. However, it's not really a symmetry. Okay, it's not really a symmetry. It is we should say it is too many. I mean, duplication. I think that's the word. The duplication of the representation of physics. Okay, yeah, and Janice, probably you will need to wait until Professor Chen talk about the path integral to understand what I'm talking about here. We call it the duplication of the representation of physics, because that is because for the gauge theory is not just a symmetry, because it tells us that for a certain state we have more than one description. We have more than one description to describe a state. Okay, and this point is not made clear until people try to quantize or do the quantum field theory of gauge theory. Okay, and that's the part Professor Chen probably will cover using the path integral way of quantization in next semester. Okay, so stay tuned. You will learn it very soon. But today I'm going to give you the older version, simpler version, more straightforward version of gauge theory. Straightforward means you probably don't quite get to the deepest point, but it's simple. It's so simple and intuitive. Okay, so that's why. Back to my topic. So that's why most of the more sophisticated textbook, when they describe gauge theory, they become very, very sophisticated. Okay, they use the language I told you. Yeah, and therefore it's not very, very clear, and it's not very intuitive, especially for the first-time learner. It's too difficult. Okay, so for first-time learner, I will urge you to use this older textbook, because it's simpler, it's more intuitive. Until you learn the path integral well, after you learn the path integral well, then you go back to learn the more sophisticated part of the gauge theory. Okay, and you probably will enjoy it and see what I'm talking about. Okay. Anyway, so what I'm going to present to you today is a more intuitive way of understanding gauge theory. Okay, and it's older way of it. Okay, so I will go directly to this textbook, the Gauge Theory of Elementary Particle Physics, and just to tell you that it's very useful. And let me show you here. So it dates back. Oh, sorry, Professor Chen is at Missouri, St. Louis. Okay, and Professor Lee is Carnegie Mellon, and it dates back to 1984. Not that old, but it's already 40 years old. Okay, now let me skip all the other, and it talk about a lot of things, including the quantization, including the renormalization group, blah blah blah. Okay, so I'm going to skip all this, but it's for some parts this textbook is very useful. Let me go directly to the local symmetry. We call gauge symmetry local symmetry. Of course, gauge symmetry is presented as a symmetry when Professor Yang Zhengnin invented this idea. Okay, and still it's the easiest way to understand a gauge symmetry. But let me remind you one last time, it is not really a symmetry. Okay, it is actually, as I say, it's a duplication of how we can represent a state. Okay, we have more than one way to represent the physical states of a field. Okay, but the idea is very simple. We usually start with the Lagrangian, the Dirac by spinor Lagrangian. Okay, so here I have the free electron field Psi X. Okay, this is we call Dirac by spinor, and this is Lagrangian. I'm not sure if Janus have learned this before. If not, I'm going to cover it next week, because next week I want to talk about the left-handed and right-handed thing about the stuff before I go into the standard model. So if you are not familiar with this thing, that's okay. I'm going to go ahead and talk about. Today, you just think of this Psi as a field, okay? Because this field, there is a X space-time dependence. And this partial mu is the derivative, space-time derivative, okay, of the whole thing. So this is just a number. We call it the Lagrangian. Okay, I'll call it Lagrangian. So if Janus are not familiar with this Lagrangian, yeah, that's okay. Just treat it as a mathematical question. Okay, so this Lagrangian we use it to describe free electron field. This is the free electron field. Okay, so that's the field we use to describe electron. Okay, so this electron, we call it Dirac by Lagrangian, Dirac-Lagrangian. And this Dirac-Lagrangian has a very simple symmetry. When I say symmetry, I mean when you do a transformation, look at this arrow here. When originally the field is Psi, then after transformation, it becomes Psi prime. And Psi prime is related to Psi by multiplying it with a phase, exponential minus I alpha. Here, this alpha is a constant. This alpha is a constant. So it is just, remember this Psi is a field. Okay, so it's everywhere. Then you multiply the Psi everywhere with a number. Not really a number, a phase, exponential I alpha. And everywhere is multiplied by, is the field at everywhere is multiplied by the same number, because this, I say this alpha is a constant. Okay, so that's the whole key. So we usually call this, and you can check if this Psi is multiplied by this, after transformation is multiplied by this exponential minus I alpha, then we got a, please look at my, yeah, you can see my pointer. So there is an exponential, the minus I alpha here. And then psi bar, because it's a complex conjugate, then there is an exponential I alpha here. Okay, both of them are independent of space-time, so that we can just treat them as a constant. So the two multiply, they cancel each other, becomes 1. Okay, so that means before the transformation, that's a Lagrangian, but after the transformation, we still get exactly the same Lagrangian. Okay, so in that we will call it, the Lagrangian is invariant under this transformation. Okay, so that's why we call it invariance. Okay, and because this alpha could be any number. So if you are familiar with group theory, then this e to the minus I alpha actually has infinite items in it. Okay, and if you collect all the possible transformation, they form a group. Let me put it in Chinese. 假如你把所有的这个变换都把它收集起来，那么你得到的呢就是一个群。You collect all the transformation together, it forms a group. Okay, and this is very, very mathematically very sophisticated. So you probably you need to think about what I'm talking about here. You collect all the transformation and they form a group. And this group, because it's just a phase. It's just a phase. So it's actually, we call it a U1. We call it U1 because all the elements in this group commute. Okay, it doesn't matter. You multiply one phase with the other, or you reverse the order of the two. Okay, they give the same result. So this kind of group, we call it abelian group. Abelian group. Okay, so an abelian group has only one kind. We call it a U1. Okay, so this is U1. Of course, if you want to be more go detail, then you can go back to the group theory to check what we define by U1, what we define by either I alpha, things like that. And I believe at Griffiths, you don't need to go very far. Griffiths, I'm elementary particle, the second edition of Griffiths. I'm going to talk about this book later, so let me just mention it in passing. This textbook actually tells you a little bit about, if you only need a little bit of group theory, then this book is good enough. Okay, that's a textbook for the senior elementary particle introduction. Elementary particle physics introduction. Okay, so it's very, very simple. So you are not familiar with this definition, like U1, like symmetry, like global, these things, you can go back to check in that textbook. Okay, because it's very simple. Okay, so back to our discussion. So this is called U1, and this U1 symmetry is for this. Let me put it out again. Then this Lagrangian is invariant under this U1 transformation. So we call it, this system has a global U1 symmetry. It is global because this alpha does not depend on space and time. It's the same everywhere. It's the same everywhere. Okay, so this global U1. The global U1 symmetry is actually a standard topic in quantum field theory. And I believe Professor Chen will, of course, talk about what will going to happen with global U1 symmetry. Let me just mention some result. You will have a current, a conserved current, that is a conserved current. In this case, it corresponds to the electric current and electric charge, things like that. Okay, it's called Noto Theorem. Okay, usually Noto Theorem is the first topic you are going to encounter when you took a quantum field theory course. Quantum field theory course. Anyway, so I'm going to leave that for Professor Chen to cover it. Just remember, if you have this kind of symmetry, then you have a conserved current. Let me put it in Chinese. 假如你有 U1 的对称的话，你就有一个这个电流的守恒。不对 ，current 的守恒 ，current 守恒中文要怎么说 ？Yeah, I couldn't put it in Chinese actually. Okay, so it's a conserved current thing. Now, just imagine some of the physics are crazy, and somehow they are dreaming about enlarging this symmetry. They say, Well, it's a localized world. It's global, I know, but globalization causes a lot of trouble for everybody, right? And so I want to stay local. I don't want to be global. Okay, I cherish Taiwanese culture. I cherish Filipino culture. I don't want to be globalized so that everybody is the same. Right. Why? Does every field transform by the same phase, multiplied by the same e to the minus I alpha? Could I have my own alpha? That's the point. So why couldn't I replace this alpha with a alpha function here? Please look at my pointer. So why can I not replace the constant alpha with a alpha function, which depends on space and time? So that's called localized, because every different places, then the alpha is different. We can choose our own symmetry. Of course, actually, it's not about localized. So here, this kind of language is actually some kind of a popular science language to cheat you into believing that you understand. It's fun. Actually, what's important is not this alpha depends on space. It is this alpha depends on time. But the point is, if alpha depends on space, then it depends on time. This is the point most of our textbook missed. So let me just emphasize it one more time. This alpha depends on space. It's not very important. It's not important. However, because you are working in relativistic quantum field theory, so if this alpha depends on x, the space, then it definitely depends on time. Okay, it is the fact that this alpha depends on time that make the whole thing becomes very complicated. Okay, becomes very complicated. So that's in a sense the essence of gauge symmetry. This alpha could depend on time. Okay, remember when we use this Lagrangian, I want to determine the future of the evolution of this field per se. Okay, so it is the evolution. It's the dependence of per se on time that is of interest to us. However, if you make a transformation like alpha that depends on time, that means you can at different time you can adjust your per se using the phase. Then you ruin the whole thing. See, because you kind of transform their future or transform their destiny. Originally, it followed this path. But if you have the freedom to transform the original path into another path, remember, alpha could depend on time. So you can transform a little bit at the beginning, then larger in the middle, and then again a little bit in the end. So you change the whole path into another path. Okay, so that means, but on the other hand, if this symmetry is really a symmetry, then that means this original path and this transformed path actually represent the same thing. So that's why we call it the duplication of representation. Okay, so it's a little bit away from our presentation. So don't worry about it. But the point is, the alpha depends on time is actually the key essence of the gauge symmetry. Okay. Okay, but with that in mind, if this alpha could depend on x, you probably will respond right away by saying that if alpha depends on time, if alpha depends on x space time, then it is not invariant anymore. It's simple. Because if alpha depends on x time, then per se bar. Again, I multiply this per se bar. Oh, sorry, per se. I multiply this per se by a phase exponential minus I alpha x. However, this when you put this per se into the Lagrangian here, this is the per se. You put it into the Lagrangian. This one. So originally, this is the kinetic energy term. We usually call this the first term, the kinetic energy term, although it is not really a kinetic energy. But anyway, it's a common mistake. So if you put this kinetic energy into the transformation, it becomes prime and prime. However, this C prime is exponential minus alpha x times Cx. And when you put this into the derivative, it actually has two terms because alpha is a space-time dependent. Okay, this is quite different from the 8.2 when this alpha is a constant of space-time. When you do the derivative, then it gives you a zero result. However, here, because this alpha is space-time dependent, so that means when you do this derivative, then there are two terms. The first term is what you will expect, but the second term is alpha, the space-time derivative of alpha. Okay, so this time actually is additional. Okay, that means this time with this term, that means this Lagrangian is not invariant. Okay, it's not invariant because here this first term equal to the original form, and so this item actually give Lagrangian, which is not invariant. Okay, so remember this form because later I'm going to kill this term by adding one more term in the 8.1. Okay, so there are two ways to deal with it. Usually our teacher will tell us there are two ways to face this. First, you can say that, okay, so that means you don't have localized symmetry. Fine, then let's get off. Then we can go back home. We don't need to work anymore. And there are second way to face this problem. If I insist on having a local symmetry, could I try something to make it happen? For example, can I add something on 8.1, the free Lagrangian? Can I add something? Can I add something so that this term, the additional term that after transformation could be canceled out? That's the point. And actually, it's very simple to see that we can do that. And and this has been known for quite some time. I think right after the quantum field theory, the quantum mechanics, the Dirac Lagrangian is invented. This was discovered by Weil. Okay, and also I think also by other people. Okay, so it's a very, very old trick. The trick is that it say here, I need to replace the partial derivative with respect to space-time by this we call gauge covariant derivative, the capital D mu. Okay, if I replace this with this, and could we design this D, this covariant derivative, so that the Lagrangian is invariant? Okay, so how to design the thing? How to design the gauge covariant derivative? Actually, we need to ask ourselves, what purpose do you want to serve? What we want to serve, let's go back to 8.1D. Let's go back to 8.2. If this alpha is space-time independent, is a constant, then the derivative of psi after transformation, you only need to multiply it by the same phase, e minus I alpha partial mu psi, okay, after transformation. So that means the derivative, space-time derivative of psi actually transform in the same way as psi itself. Let me say it again. The derivative of psi transform after the transformation, transform in the same way as the psi itself. However, that's not the case for the local symmetry, the local transformation. After the local transformation, we got one more term here. That's what I told you before. Then, so if I can design this D covariant derivative so that after a transformation, it also transforms like the field itself, then we can accomplish our job. So that means our requirement is that this d mu, capital D mu psi, after transformation, it becomes itself multiplied by the same phase, exponential minus I alpha x. Please observe that this transformation property is the same property shared by psi itself without the derivative. Okay, so if I can accomplish this, I can simply replace this derivative by capital D. Then after transformation, the capital D psi will be multiplied by a phase, and the psi bar will also be multiplied by the inverse phase. And the phase and the inverse phase will cancel each other, and then we get an invariant Lagrangian. Okay, so it's a little bit awkward and cumbersome to describe on screen, but you can try to understand this yourself when you look at the textbook. Okay, sorry about that because we cannot do it in person. So it probably is easier to understand if I have a blackboard to write and things like that. Okay, it's a bit awkward to describe in words. But if you can, I give you the PDF file of this textbook, and you can check this 230 page P230, then you can probably follow the description. And trust me, it's actually very easy to understand. Okay, because this textbook is pretty pedagogical. Okay, so now I hope I try to convince you a little bit. That our requirement and our goal is to design a covariant derivative so that after a transformation, it transforms in exactly the same way as the field itself. Let me put it in Chinese. 我们希望设计呢，就是这个 covariant derivative，OK， 它在变换之后，它的变换方式呢是跟这个场自己是一样的 ，OK？ 那场是怎么变？场就是你把这个 psi 呢乘上一个 phase 嘛 ，OK？ 好，所以呢你的变换就是这个 derivative 乘上一个 phase。那么我如果能够做到这件事情，那我就已经找到了一个可以让你的这个 Lagrangian。那这里有写好，所以呢这个 psi bar d psi 那就会是 gauge invariant。Sorry, I didn't see this line. So if I can do this, then this combination psi bar d mu psi will be gauge invariant. Okay, and this combination is exactly the Lagrangian kinetic energy term this, but with partial replaced by the covariant derivative. Okay, so it's quite simple. Now I still need to tell you, could we do that? Could we design our covariant derivative this way? The answer is yes, but you need to introduce a new vector field. Okay, it is a vector field, means the field has 4 components, 0, 1, 2, 3. So it's A mu x. So this new vector field, we call it gauge field. So the bottom line is if you want a gauge symmetry, then you need to introduce a new gauge field. This gauge field is new. It's not something that is hidden behind. Okay, so as I told you, if you do not introduce this gauge field, then you won't be able to get a local symmetry, as I showed you in the earlier page. But if you insist on having a gauge symmetry, you need to pay some price, and that price is that you need to have a new gauge field. Okay, so as the mathematics is quite simple, you can simply design the derivative, the covariant derivative capital D as partial mu plus IE a mu. So that's why it is a vector field, because it needs to match the partial derivative with respect to the space-time. So if you define it this way, and you define this A to transform in terms of 8.7. 8.7 is that its transformation property is it adds another term. Usually when you have U1 symmetry, then you will multiply by a phase. That's the traditional transformation property. So that means gauge field is not a traditional field. Okay, so after the transformation, it is actually added another term. And this added term will be designed to cancel the extra term we get from the derivative in 8.4. Okay, so it's not hard to design how A is transformed so that the extra term will cancel exactly this one. Okay, and the result is that this A this A transform like A mu prime equal to A mu original field, but plus 1 over E partial mu alpha x. Okay, so you can also see that if alpha is a constant, then this term vanish. So for global symmetry, the A will just transform into itself. Okay, so it does not transform. So that's why we don't really need a term if you only want global symmetry. But if you want the local symmetry, then this term will appear so that this vector field or gauge field do transform under the gauge transformation. Okay, so you please check by yourself if you design this A transform in 8.4 equation 8.4, then this d mu will have the right property as I have here. So 8.7 put it into 8.6 will give you 8.5. That's the point. Okay, and if I have blackboard, I can do the calculation for you. Unfortunately, but you can do it at home yourself, so it's not that difficult. Okay, sooner or later you can also visualize it when you read the text. Okay, now finally, so this d mu, as I told you, if I replace the partial mu with d mu, then originally let me show you original Lagrangian again. Oops, sorry. So that's the original Lagrangian. This partial mu replaced by capital D. Then this capital D has two terms. One is partial mu, so return to the original form, but that has one more term, which is A psi bar psi. Okay, so I hope this convinced you. You can do it yourself at home, that the Lagrangian now is this. So this and this, the first term and the third term are the original Dirac free field, but this term, the additional one. Janus asks, is the form of A fixed? What do you mean by form? I think you are talking about this 8.7, right? If you are talking about 8.7, yes, it is fixed. The transformation property is fixed. Let me wait for Janus. Does that answer your question? Because I don't understand the form of A fixed. What is fixed in this sense is this transformation property. So this 8.7 has to be fixed. Okay. Different representation of A. Well, if in U1 you only have one representation, okay, in U1. However, if we are talking about SU2 or even more complicated SU3, then that's right. Then this A actually I think I probably will talk about that next week. However, as you know, I can push forward to the non-abelian gauge theory. Okay, so if I push over to the non-abelian gauge theory, SU2, then you see that, and you probably have known already, this A actually has 3 copies. So here, you got A mu I. That means there's I equal to 1, equal to 2, equal to 3. There are 3 copies of gauge fields. Okay, so in that case, you can also form linear, and this AI is a 3-dimensional linear space. Okay, so that means you can do any linear transformation. You can have a different representation of A. I think that's probably what you are talking about. Yes, in that sense, the AI has 3 components, and those 3 components can mix with each other in the sense that the linear transformation could perform on a linear space. So this AI then form a linear space, right? Then they could have different representation. However, that's in the future. That's next week. So that's USU2. But here, A, we only have one. We got only one gauge field. So that's only one guy. Okay, so that means you don't have any other choice. Okay, and A mu, this mu is 0, 1, 2, 3. You cannot mix them because that's the 0, 1, 2, 3 are the index for relativistic. That's the time component, the space x component, space y, space z. So you cannot mix them. You can do Lorentz transformation to mix them, but it only has one representation. So A, there's only one A. In this sense, for U1, I don't the form is fixed. I think probably that's the answer. Okay, but for non-abelian gauge, no, for non-abelian gauge theory, then you can have more than one representation of the gauge field because there are more than one gauge field. Okay, perfect. So very nice. So you are getting the point, and great. So, and yeah, for every particle physics, you need to do the exercise. As I told you, if I have a blackboard, then I probably will go out to write things on it. But since we don't have, you cannot do it online, and you are encouraged to do this very, very simple mathematical manipulation at home. And as I say, it's very simple because there are not many pages. Okay. Now we are almost done, okay, with our presentation today. So 10 minutes more, okay. Let me summarize. Now I have constructed already a local symmetric Lagrangian. This guy, A point A, with the addition of this term, psi, A psi, with the addition of this term, then we will have a local symmetric. With this Lagrangian, sorry, because it's sometimes very hard to pronounce this in English. So this Lagrangian, the new form, with the addition of this term, it has a local symmetry. Not just global. Of course, it still has a global symmetry because you can assume that this alpha function is a constant. So it's still global symmetric. However, it is even more powerful than the original one because it has a local symmetry. This alpha could depends on the space-time, as I mentioned several times during our presentation. Okay, so Lagrangian. And let me point out one thing. And after you learn quantum field theory, you know that with quadratic term, this one without the A, this one, and this one, with quadratic term, you get a linear differential equation or equation of motion. Okay, so we call it free field. Free field means that it satisfies the field or the particle or the wave, whatever way you want to call it. Then they satisfy superposition, linear principle of superposition. Okay, so usually we'll say that when the two light wave or two light ray passing each other, okay, they don't interfere with each other. When they pass then they will resume their original propagation. We call it the principle of superposition. So that's the free field. That means the particle just propagate without any interaction. No interaction means free. So that's with quadratic field, with terms with quadratic field, then we have a Lagrangian for free particle. However, if you look at the additional term we have here, it is psi A psi. So it's not quadratic. So it's not free. It gives you the interaction between A, this new gauge field, and the psi. Okay, so it's an interaction term. So that's why gauge field theory is a give you interaction term automatically and actually fix the form. Remember, when I write the form in this way, this IE could not be chosen arbitrarily. For example, could I choose write it as a 1/2 of E? No, you cannot do that. If it's only 1/2 of E, then the additional term of this will not cancel the additional the extra term. Here. Okay, so in order for these two extra terms to cancel each other, that means this coefficient, sorry about that, I'll improve my skill next time. So this actual term, the coefficient of this term is actually fixed. It could only be I times E. It could not be 1/2 E, it could not be 1/4 E, it could not be 1/3 E. It just needs to be I times E. So this guy is the coupling constant. It's a coupling constant between A and psi and psi. So the gauge theory fixes interaction so that you don't have any choice. That's the beauty of gauge theory. That's the beauty of gauge theory. It's fixed. It's fixed. You don't have choice. I don't know why physics want to be fixed and without freedom, but it is kind of beauty because it means the God has made the choice for you. You don't have any freedom to do any deviation. Okay, so I personally find it is very, very attractive. Okay, so let me emphasize this thing. Okay, so gauge theory, you introduce a gauge field. You not only introduce a new particle, you also introduce the interaction between this particle and the original psi, the Dirac electron. Okay, so I think that's the beauty of the whole thing. Okay, so but here let me finish. Okay, so let me finish in 5 minutes. So when I say I introduce A, you can ask, are you sure it's a field? Well, it's a field because this thing, it depends on X, space and time. However, a field needs to have its own Lagrangian or it needs to have its own kinetic energy term. Do you have that? No, not yet, because this A has only this term to appear in the Lagrangian. No more, not yet. So you need to add something. That's what I have in mind, 8.9. You need to have something which consists of only A itself, and it is quadratic, and it has two derivatives. Remember, every kinetic energy term is quadratic with two derivatives. Okay, so we need a Lagrangian, which consists of 2A quadratic and two derivative, and also gauge invariant. The final thing is most important. You need to a gauge invariant term, which is give you the kinetic energy term. Okay, so in this case, this term is very easy to be found. Okay, you simply need to form this combination partial mu A nu minus partial nu A mu. For its convenience, we also call it F mu nu. It is an anti-symmetric tensor. Don't ask me how people found this. Actually, I'm going to tell you later. Okay, but anyway, just follow me a little bit. This F mu nu, we write it as a partial mu A nu minus partial nu A mu. Okay, so it's anti-symmetric. Anti-symmetric means if you interchange mu with nu, then you get a minus sign. Of course, if you exchange mu with nu, then this term becomes this, and this term becomes this. So you got a minus term, obviously. Okay, so my point is, if you define this f mu, you can ask, how does this f mu transform under the gauge transformation if A transform in the way of 8.7? Let me put it again. If A, the gauge field, transform in the way of 8.7, how does this F transform? The answer is, it does not. That's the beauty. You can try to put this into this. Okay, so after transformation, this term will give rise to an additional partial mu, partial nu, alpha. This term will give you an additional partial nu, partial mu, alpha. But you know the derivative could interchange the order. Okay, so partial mu, partial nu, alpha minus partial nu, partial mu, alpha cancel each other. Okay, wow, it's awkward to pronounce, but wow, you can check it by yourself. But my claim is, and you please check, if you put this form into here, f mu nu prime equal to f mu nu. So that's why you say here, f mu nu is in fact gauge invariant by itself. Okay, so if f mu nu is gauge invariant, of course this combination f mu nu are also gauge invariant. Done. So this f mu nu, please remember it because you are going to encounter it so many times, which is the kinetic energy term of the gauge field. This needs to be put in by hand. It need to be put in by hand. If you don't have this term, this original A.A, we cannot call this a particle because it is only a field. It's only a field. It could be a classical field. It doesn't need to be propagated at all. A could be any number, okay, as long as they transform in this way, okay. But with the addition of this kinetic energy term, A is given life. A is given life. It becomes a particle because this is the kinetic energy term, okay. So with this kinetic energy term, then this A becomes a particle, and this particle is photon. This particle is photon. So this term give you the interaction between the electron and photon. So it is called QED, quantum electrodynamics. It's a prototype quantum field theory. So in the old days, when we say we learn quantum field theory, what we mean is you learn QED because it's a prototype. Okay, so this again 8.8 plus 8.9 is the content of quantum electrodynamics. Okay, I'll leave it to Professor Chen to tell you how it works and how to write the Feynman rule, how to draw the Feynman diagram. That's not my job, but well, quantum electrodynamics. Before I let you go, I think I'm over optimistic. I'm going to tell you some of the details like yeah, maybe I can mention it before I let you go. This A mu. Usually, you can ask, this photon, does it have mass? It is your job, and I can show you a little bit why this f mu nu give you the Lagrangian, give you the kinetic energy term. But it is missing a mass. Usually a mass comes in the form of this. M times A mu. It's a standard quantum field theory exposition to have a mass term to tell you that this is the mass term of the vector field M A mu. Okay. However, as this feature, Professor Lee emphasized, this term is not gauge invariant. You please check yourself, but it's so simple. because here I have already tell you how A transform. It get an additional term. If it get an extra term or additional term, then A mu will get 3 more additional terms. So of course, it's not gauge invariant. Okay, so it's a very, very, very important property that if this vector field, this gauge field is gauge field, then it is massless because the mass term is not gauge invariant. Okay, so this point 1 is so important. Okay, so important. Fortunately, photon really is massless. Photon really is massless. So the first quantum field theory is a gauge theory, we know. The quantum electrodynamics, QED, is indeed a gauge theory. Okay. So before I let you go, I want to show you how people found this in the first place. For example, this form, F mu nu. How could you know that this is Lagrangian? How do you come up with this? Actually, it's very simple. If you go to this Griffith's book, I'll show you the cover later. Okay, so this F mu, you see, that's the same thing. This A mu, it actually, if you took, probably Janus did not, but I think if you, but you can go back to took some electrodynamic, classical dynamics, classical electrodynamics, then this A mu, you should be familiar with this A mu. This A mu is actually the combination of V, the electric potential, and vector potential, A vector. Okay, we usually call it vector with an arrow on the top of it. Okay, so if you combine the vector potential with V, then you get this 4-vector form of A mu. Okay, and it is easy to see that. Wow, it took some time. The best way is to look at this this textbook, the presentation of this book. Actually, this F mu nu is the electric field. Okay, you only need to check 7.77 and 7.78, and you see that this E is actually part of the F mu nu. So this F mu nu is not anything new. It is just electric field and the magnetic field. So that's why this F mu nu, the thing I wrote you before, this F mu nu here, okay, is actually a combination of electric field and magnetic field. And it is easy to see in this way. Okay, again, you probably need to do it yourself to see the beauty of it. Okay, it is no use if I do it on the blackboard. Okay, and you can see that, yeah, and F mu nu is actually electric field. So all the Maxwell equation can be written in this very, very simple covariant form. And then let me find the F mu nu, and here is another presentation of the gauge field. So you can consult the two books and see how gauge field actually works. How come I didn't find F mu nu? It's very strange. Sorry. Well, F mu nu. So the combination of F mu nu. That's weird. I couldn't find the formula. Sorry about that. But if F mu nu is electric field and magnetic field, then this thing, F mu nu, this combination is actually E squared and B squared. Okay, if you took a general physics, the freshman, the general physics, E squared plus B squared are the energy of an electric field, of an electromagnetic field. Okay, so that's how people, and so people first write down the energy of the electric field and magnetic field, so E squared, B squared. Okay, and then they use it to write down the Lagrangian of the Lagrangian of the electromagnetic field, and they find that E squared minus B squared. And if you put everything together, you will see that this is exactly E squared minus B squared. I couldn't find, but I think I have it in the Griffiths book. Somehow I couldn't find it here, but you probably could find it yourself. E squared, B squared. No, still no, but probably I'll find it out next time to show you this. Okay, so yeah, that's what I have to say today. Next week, I will try to extend this presentation to non-abelian gauge symmetry. Okay, so next time, this field will not be just only one. It will be form a doublet. So per se 1, per se 2. So it's a doublet. Okay. So the transformation will not be a phase. It will be a matrix. This we will call SU2 transformation matrix. Okay. We'll see how we can do the same thing in this kind of setup. Okay. And the answer is not very, very different from what we have today. We again need to define a covariant derivative. However, the mathematics are quite the same. Okay, just a little bit more calculation and manipulation. Okay, so it will be helpful if you have time to read through this couple of pages. Okay, so you can see that the gauge theory could be covered by only 3 or 4 pages. Okay, so it's very, very simple. Okay. That's it for today. Okay, and yeah, next week I will talk about non-abelian gauge theory, and I'll put all the material and the page I assign here on a course page, course web page, and I'll send the address to all of you. Okay, so I haven't established yet, but I'll do it probably tomorrow and send you all the stuff. Okay, in between. Yeah, thank you for being with us today. 谢谢大家. Okay, and we will stay in touch and see what I'm going to do with the rest. Okay, so again, thank you, Janice and David. But we still have one more participant. And as I say, this course, as you can see, that this course really require 这个 quantum field theory。 OK， 好，所以修课可能是对，如果不是对做基本粒子的人来讲，可能是没有太大的用处哈。所以呢，这很抱歉，在一开始的时候没有把这件事情讲得很清楚。OK， 好，所以我希望今天看完以后，你大家就知道，这可能还是要做基本粒子物理的人才会有用。Yeah. Sorry, I'm telling people that you really need quantum field theory to start, and this is only designed for particle physicists. Okay, so I'll see you next week. Next week I probably will go back to the original time at 1:20. Okay, but it doesn't matter if you log in at the right time, because the video will be saved on my channel, so you can read it, you can listen to it anytime, maybe before your bedtime, or because it's very it's easy to sleep under my song, right? Okay, so see you next time. Bye bye.